Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at some examples of dynamic programming, and in particular we will be looking at longest common subsequence. In the last few lectures, we have seen various problems and various techniques of solving them. Some of the problems has to be reduced to some other problem, for example, some graph problem, and for solving some problems and some graph problems, we have to apply various techniques. We have seen recursive algorithms, we have seen divide and conquer algorithms, we have seen dynamic programming algorithm, and we have seen greedy algorithm. A natural question to ask is that for which problem which technique should be applied, or which problem should be reduced to graph problems, and so on and so forth. There is no simple answer to that question. This is exactly where research comes in the picture. This is what one needs to do by practice, understand by practice what is the right technique to apply, what is the right approach to go for handling these problems. The best way of understanding or having a good understanding of how to approach these problems is by trying out more and more examples. So, in the next few lectures, we will be look at various examples of problems and try to understand which of these approaches should be used for these problems. For some problems, there is some hints can be given about when some particular technique should be applied and when some particular technique will not be helpful, but again these are very heuristic arguments. There is no proper understanding of which problem needs to be solved using which technique. So, for today's lecture, let us start with this problem of called longest common subsequence. So, given two sequences of symbols, we want to determine the longest common subsequence between these two strings. Now, a subsequence is simply defined by you take this original sequence and drop some of the symbols from that sequence. So, that is a subsequence. Note that a subsequence need not be contiguous, it is not like a substring, it is can be anything. So, what we want is that we want a subsequence that is a subsequence of both these given sequences. So, let us look at some examples. So, here is an example. Say the string 1 is called mathematics, the string 2 is education. Now, what are the subsequence of mathematics? Note that I can choose any number here. So, I can take M, T, H, E, T. So, M, T, H, E, T is a subsequence of mathematics. Now, is there a common subsequence of mathematics and education? The answer is no, because by no way I can drop some symbols from education to obtain this thing M, T, H, E, T. So, what about something else? Say A, T. A, T is a subsequence of mathematics and is also subsequence of education, A and T. Note that the ordering of these symbols in these two sequences matters. So, A, T is a subsequence of both mathematics and education. Now, we are looking for the longest subsequence. For example, here I can also look at E T I, E T I. See, the earlier one A T was a subsequence of length 2, and now I have a subsequence of length 3. So, clearly this is a longer subsequence than A T. So, E T I is a possible long subsequence, but can we make it bigger? The answer is, in this case you can go over this whole thing and try to see that if I make A here and A here. So, E A T I is a subsequence of both mathematics and education. So, here we have a subsequence which is of length 4 of both mathematics and education, but who guarantees us that this is the longest common subsequence? It is not easy to check. It is true that for this, in this setting, the longest common subsequence is indeed E A T I, but we need to verify that, we need to prove it, or need to find it, and this is the problem that we have. Let us look at another example. Say we have examples villages and cities. Again here we can have things like I and E, I E, I E. This is a subsequence, but again I can also have I E S and I E S. These are also a common subsequence between villages and cities. So, again this is a subsequence of length 3 between these two strings villages and cities, and I would need to look at what is the longest common subsequence. In this case also the longest common subsequence, or which we call LCS, is EIS. Now, there can be multiple longest common subsequence, there need not be a unique longest common subsequence, but we are interested in finding one such longest common subsequence, a subsequence of length k such that there does not exist any subsequence of length k plus 1 which is common to both the strings. This is the problem of finding the longest common subsequence. This problem has enormous applications. It has applications in computational biology. We have been, say, we all know that every living object has a particular DNA sequence, and one interesting thing to note look at that how different are these two animals by looking at the DNA sequences. To understand that, one needs to understand, is there any common similarities between these two sequences, and that is where this problem comes a lot, called the longest common subsequence. It has been used to predict evolutionary histories of species, and it is, as you can see, it is one of the most important and interesting problems that one can think of. So, a formal statement is as simple as that. Given two strings or two sequences A1 A2 to AN and B1 B2 to BM, note that these two strings need not be of the same length. We want to output the longest common subsequence of these two strings A1 to AN and B1 to BM. Now, how do we do it? That is the question that we want to ask. When we come to such kind of problems, there are few things we should try out. We should try out our greedy approach, the brute force approach, the recursive approach, the divide and conquer approach, the dynamic program approach, all the approaches, and it is not very clear as at the start which one would give me a better algorithm. So, let us start with the first attempt. The first attempt is the brute force approach. So, what is the brute force approach? So, we have this string A1 to AN. We can check all the possible subsequences of A1 to AN. Now, how many subsequences are there? Now, note that a subsequence is comprises of these elements A1, A2 till AN. Any one of them can be taken or not taken. So, I can either take in my subsequence A1 or not take, A2 I can take or not take, AN I can take or not take, and under a particular sequence of taking and not taking, we will get a subsequence. So, the total number of possible subsequences is of form 2 to the power n. For everything there are two possibilities. Now, once we have a subsequence, we need to check whether the subsequence is also a subsequence of B1 to Bm. Now, that is not that hard. I leave it to you as an exercise, but if I give you a sequence, say a subsequence of A1 to An and ask you to check is that one a subsequence of B1 to Bm, how would you do it? It can be done in linear time. All you need to do is go over this subsequence that we are looking at, one from left to right, and accordingly do it. Now, once we are done with that, so every possible subsequence of A1 to An, we check whether that is a subsequence of B1 to Bn, and now after that we will have the list of all the subsequence of A1 to An which are also a subsequence of B1 to Bn, and output the longest subsequence. So, of course, we will be outputting some common subsequence, and that would be the longest one. The idea is simple, clear, and the algorithm is simple. But what is the running time of the algorithm? As we are told, the number of possible subsequence is 2 to the power n. So, the runtime of this algorithm is 2 to the power n. This 2 to the power n is a very bad term. It is something that is exponential in n, not a polynomial in n. So, this is something that is not good for us at all. So, question is that how can we go about it? So, brute force approach does give me the right answer, but it takes a lot of time. Question is that can we do better? As we know that one of the approaches to take is the recursive approach. When you try to do the recursive approach, we have to define different function that can be recursively called. Say here is the function LCS ij, let this be the longest common subsequence of the string A1 to Ai and B1 to Bj. Now, why did I define this LCS ij? Of course, at the end it is defined such that it can be useful for me, but more importantly this is something that we have understood from various attempts that we have made in the last few lectures about how can we define this particular problem or sub problem that can be used for recursive calls. Now, clearly if we have to solve the longest common subsequence, we have to call the LCS NM. LCS NM will basically be the answer that we are looking for. So, let us start with this. What is the base case? The base case is that if any one of the term is 0, 0 basically means that this string that we are looking at, say in this case k is 0, means what is the longest common subsequence of A1 to Ak and the empty string. If it is the empty string, then there cannot be any longest common subsequence, and hence it will be the empty string, and similarly LCS 0 k. So, this gives us the base case, and we know final thing that we are looking for. So, now we would be going for the recursive call to LCS. We will have a short break now. After the break, we will see how to do the recursive definition of LCS. Welcome back after the break. Before the break, we saw how to define the LCS ij, a function that hopefully will help us to recursively solve the longest common subsequence problem. We saw the base case, but let us look at the how can we define the recursive calls. Consider these two strings villages and cities. The output that we are looking for is LCS 8, 6. Now, note that the last symbol here are same. So, what does it mean? It means that if I have a longest common subsequence that ends before s in both of them, then I can add s to both the subsequence and we will get a longer subsequence. Or if the longest common subsequence of the villages say includes s from the villages and does not include s from the cities, the s is the must be there before this last one, and so there must be another longest common subsequence which will be using both these s's. So, in other words, the longest common subsequence will surely be, or rather there will be a longest common subsequence that would surely be using this s. So, what we have is that this LCS 86 can be written as, so I have this last one that anyway I have used, and whatever the longest common subsequence of the earlier two things are, which is 7 comma 5. So, that is the recursive call, because if the last term is anyway same, then we can use that one simply. Now, let us look at the next one, say the E. Again the same kind of argument holds. The longest common subsequence for this string and this string, I claim that must use these two E, because if they do not use both these E, then I can add this E at the end of the both of them and obtain another longer common subsequence, which is not possible. And if it uses, if the longest common subsequence uses the E from one of them and not from the other, I can just change this sequence in the second string to obtain, to use both the last E's. So, same argument, basically what we obtain is that LCS 8 comma 6, which is LCS 7 comma 5 plus 1, which we had got, can also be written as LCS 6 comma 4 plus 1 over here. So, I have LCS 8 comma 6 will be LCS 6 comma 4 plus 2. Now, let us go to the next one. Now, here has the interesting part. Say here is I and here is this G in the end. Clearly, the longest common subsequence cannot be using both of them. So, either they will use the G or it will use the I. So, if it uses the G, then it cannot use the I, because there is no I to be used at the end. So, in that case, this must be a longest common subsequence of this and this, and if it does not use G, then it might use I, then I will be using this. So, in other words, this LCS 6 comma 4, that is what we are looking at, can be written as the max of the longest common sequence in which you do not use G, you might use I. So, it is LCS 5 comma 4, and the other one where you use G, but then you do not use I. So, it is LCS 6 comma 3. So, this basically gives us the recursive definition of the LCS. So, the pseudocode for the recursive algorithm will be as follows. For all k, we first define the LCS of k comma 0 as 0 and LCS of 0 comma k as 0. Now, if ai equals to bj, then we know that LCS of I comma j is equals to LCS of I minus 1 comma j minus 1 plus 1. The idea is that in that case the longest common subsequence between a1 to ai and b1 to bi will surely be using ai and bj. Else means if ai is not equal to bj, then the longest common subsequence is the max of LCS of I comma j minus 1 and LCS of I minus 1 comma j. So, pseudocode is exactly what we explained, and the running time of this algorithm is, for that let us define that T n be the running time of LCS I comma j when I plus j equals to n. Note that when we call the max of these two terms, so we get T of n equals to twice T n minus 1 plus some order 1. So, in other words, if you solve this equation, you will get that T n equals to order 2 to the power n. Again, this is not good, this is still exponential, but this is where our understanding of these algorithms comes in the picture. So, note that the main, if you solve these problems by hand, and you realize that the main problem is we are doing a recursive tree kind of stuff. So, we had say I j, we are calling LCS of I j, from that we had called either I minus 1 j or we had called rather and we had called I j minus 1, and then from here I had called again I minus 2, I minus 1, j minus 1, I minus 2 and j. So, this is the next call that would happen, and what would this one be? This one be I minus 1, j minus 1 and I j minus 2, but that is not important. What is important is that this term and this term are identical. So, in other words, when we are doing the recursive thing, LCS of I minus 1 j minus 1 is being computed twice in this recursive tree. So, we are kind of overdoing this stuff, rather we are redoing our stuff. So, LCS I comma j would have called LCS I minus 1 comma j and LCS I comma j minus 1. LCS I minus 1 comma j would have called LCS I minus 1 j minus 1, and LCS I comma j minus 1 would have called LCS I minus 1 comma j minus 1. So, the same thing is being called, and if you just call the recursively, you would see that we have to solve them twice. That is not good. How can we reuse it? And this is where dynamic programming comes in the picture. We need not compute it again and again, but we can store it properly. So, we can do better using dynamic programming. And just to quickly go over the techniques for forming algorithms, we have divide and conquer algorithm, we have greedy algorithm, and we have dynamic programming algorithm. And in the case of dynamic programming, idea is to decompose the given problem into smaller sub problems. That we have done, that we do even in our recursive algorithm setting. It is this place where things become very different. We have to solve the sub problems and store the answers in a table, so that we can combine these results to solve the sub problems. So, when such a thing happens, or rather when we see that a recursive algorithm is calling the same algorithm or same function again and again, we need to store it in a table and solve it, and this is where dynamic programming comes handy. So, let us try to understand our setting. Here we define this LCS in identically same way as we have defined for the recursive algorithm. LCS ij is the longest common subsequence of A1 to AI and B1 to Bj. The base case is also same, and the combination is also same, nothing new, except that in this case we would not just call these functions, but we will store it in a table. So, in other words, we will have a table of this form, where for each item, so here we will have LCS of 3 comma 4, and that is all that we will do. Now, clearly what we want is this thing LCS of 6 comma 8, and we can solve it. How? Of course, to start with, okay, we can write down as this thing as villages and cities, that will just help us to understand it, and we can solve the best case. Note that 0, k and k 0 are all 0. Now, if you look at it and if you try to solve each and every one of them, you will see that C, you can keep on solving this one. So, LCS of this one, so rather LCS of any object, if these two are not same, it would be the maximum of the left one and the right one. So, I will quickly solve them all together. Maximum of, so C is not equal to V. So, maximum of the LCS I minus 1 j and j minus 1 I. So, it will be maximum of the left one and the up one. So, this will be 0. Similarly, this will be 0, 0, 0, 0, 0, 0, 0. Here I is not equal to V. So, again 0. Here I is equals to I. In that case, I know it will be 1 plus the diagonal one. So, this will be 1. Here again this will be not equal. So, it will be maximum of both of them, and so I will have 1 and 0. So, it will be 1, 1, 1 and 1. Similarly, here for t, again you will see that this will be not equal to anything. So, this will be 1, this will be 1, this will be 1. Here again say I, this is not equal to this one, so 0, this is equal to this, so this plus 1, so it will be 1, and this again the same thing because they are not equal, so there will be maximum of this, the upper one and the left one. For E, this will be 0, this will be the not equal, so the upper one plus the left one is 1, 1. This is the place where it will be interesting. E is equals to E, so this will be the corner one plus 1, so it will be 2, and this will be 2. And here again this will be 0, 1, 1, 1, 1, 1, this will be 2, and here these two are same, so this will be corner 1 plus 1, so 3. So thus we will get the length of the longest common subsequence between these two strings will be 3. You will clearly see that I have done it at a very fast pace, means this algorithm must be good also. I did not go over all the possible cases, because all the possible subsequence was 2 to the power n is 2 to the power 8, which is close to something like 250. So, here is the pseudocode of this algorithm. The runtime of this algorithm is, the algorithm stops after the whole table is full. This table contains mn spaces and each space takes order 1 to fill. So, the runtime is order m times n. How do you compute the table? The actually instead of the length. So, just like when we were doing it here, when we are writing the 0, if you had noticed it. So, for example, here say where I equals to I, we could have just added a arrow saying from where it was coming. So, if we had added that arrow by looking at that, by looking at just the diagonal arrows, we would have got our answers. So, we can use it to actually compute the longest common subsequence and not just the length of the longest common subsequence. So, to summarize, we have the dynamic programming that can compute the longest common subsequence of two strings of length m and n in times order m n. We would just stop with a simple question here. Here we have given two strings and we are asked to find the longest common subsequence between these two strings. What happens if we give you three strings and we are asked to find the longest common subsequence of these three strings? And more generally, can one find the longest common subsequence between k given strings? With this we come to the end of our lecture. In the next lecture we will see some more problems and how to solve them. Thank you.